Kilauea eruptions, Mississippi River sediment, and the geology of Oman. Welcome to the GSOC Geology Hour. I'm Alyssa Smith.
I'm Carrie Gordon.
And I'm Paul Hseih.
It's June already. Oh my goodness, halfway through the year. This is my Geology in a Nutshell segment where I'm going to go over some recent articles and news. So today we're going to get another Kilauea update. Done a few of those. We're going to do that. But also we're going to look at some Alaskan volcanoes. And then we're going to look at an article talking about tracking sediment in the Mississippi River. So I pulled just kind of news from mostly from the USGS, a little bit from the National Park Service because Kilauea is like this constantly changing thing right now. And then Alaskan volcano updates from the Alaska Volcanoes Observatory, so also through the USGS. So current conditions looked like this about an hour ago. The part on the left is the message they sent out this morning. But essentially right now, the activity at Hseih crater is currently paused. So nothing really going on that you can see, at least like for people that are watching outside. It's still at a current volcano alert level of watch. So keeping close eyes on it. Or aviation color is orange. So summit inflation is still going on there, and there's persistent low seismic tremors and stuff. And last night there was glow visible in the crater, but you can't really see it in just like daylight. And so we need to remember that it doesn't mean that everything's done there. It's just kind of paused and it's not actively spewing lava out. So this is a view from a few days ago. So people on the 11th of June hanging out and watching fire fountaining, which I can't even talk about how jealous I am. Just sitting at the summit and taking a look there. So a lot of locals have come out to watch. Essentially, it's just a great place to hang out and wait for something to happen. So I wanted to pull also, there's really cool imagery on the USGS website. If you look at the Hawaii Volcanoes Observatory, I'm going to share a link to this after I'm done talking. It's just a comparison of all the different episodes of Kilauea. Just that happened, I believe on Christmas was the first of them, right about then. And it has been like, I think almost weekly since then. Yeah, because 25 are about halfway through the year. There were some fountains recently that were like, I think like 1,000 feet. It was wild, coming like way out of the caldera. Really exciting stuff. And then I wanted to show what some of the active products look like. So we're still getting active molten lava. Really cool stuff. I love those fluidal textures. And if you can listen to some of the lavas, I always find that really fascinating. It's just breaking glass kind of over and over again. It's what it sounds like because that's exactly what it is. So you get a really glassy kind of film on there and it just breaks until, things cool down. So there's also some pictures of the tephra that I wanted to pull. Super duper glassy one on the left and really elongate stuff on the right. I think those fluidal textures are just really neat. And you can see kind of the state of the lava, well, now it's lava, coming out of the ground. And you can tell kind of how liquid it was at that point. And then I pulled a picture of my very favorite product of volcanism, which I never ever see. I've never seen it out in real life. That's reticulite. If you think of scoria or cinders as being like lava with bubbles in it, reticulite is kind of bubbles with scoria with lava in it. The bubble walls are really, really thin. And that's why you can see it's just this brown color. It's just glass, but it's really thin. This stuff doesn't preserve very well, so you kind of have to get it right when it happens or it just disintegrates. That's a little bit on the Hawaii volcano. I wanted to think not just about Kilauea, but kind of other things that are going on, other things that are being monitored. And so I started looking at some of the Alaska volcanoes, and two of them have been kind of a little active lately. There's a bunch that do stuff every once in a while. These are the two big ones being monitored right now. So there's Mt Spurr and great-sitkin. So Mt Spurr is currently at, there's some ongoing unrest, seismicity and stuff. And the current volcano alert for this one is advisory. So it's a step right before watch. They've been paying attention. The current aviation color is yellow. So it's kind of like, just again, pay attention, watch for things. Things could elevate, it could not. Basically, there's occasional small earthquakes occurring there, like beneath the volcano. Not really a lot of change. With volcanoes, we want to think if there's a change in like earthquakes or gas emissions, whether you have more or you get less all of a sudden, those are always things to watch for. So not really a lot's been going on there, but they still know that things are active. And why is that? Well, there's still gas being emitted. So this was just a few days ago. So this is kind of how it's been going. I mentioned the earthquakes. Here's some of the gas emissions. So this is the summit from the east during a survey on the 11th. And the yellow there is sulfur. So they say don't eat yellow snow. Usually that's not what they're talking about. They're usually not saying, oh yeah, it's sulfur from a volcano. But in this case it is. So yeah, there's a bunch of sulfur crystals you can see. Really neat thing to see. And there's steam that's coming out of fumaroles there. Fumaroles are basically the pipes that are, kicking out gases, and things get crystallized on the side. Really, really neat. And then also there's a lake that you can see if you know what to look for. It's kind of that, you can see the blue edge of it. Most of that lake is covered in ice right now. But really neat picture. Cool thing to monitor. Not doing much right now. Might stay that way, but we'll see. So the other one I wanted to look at is great-sitkin. This is such a beautiful cone. It's a composite cone, kind of the same thing, ongoing unrest, seismicity. This has been going on for a long time. I mean, a lot of standards. It looks like the current episode, period of eruptions started in 2021, and it's just been kind of like a little bit of a crawl. But that's okay. We're okay with crawls. The current volcano alert is watch, so they're paying close attention, and the aviation code is orange. So just kind of like really paying attention, making sure that things kind of stay as is, because aviation, it's a really big hazard with volcanoes. You really don't want the ash getting into the turbines. The AVO reported that slow lava effusion had continued to feed a flow, which I'm going to show in just a second. And this flow has kind of been growing, and then they've had daily earthquakes. So let's take a look at a time lapse. So this is kind of a long one. This is a time lapse photo with images taken about every 11 days from May 9th, 2011 to November, or I think it was supposed to be 2021. Yeah, it's supposed to be 2021 to 2023. I can't type, that's okay. So these images were captured using synthetic aperture radar, or SAR, and you can see the flow growing, and you got lobes that are spreading out in that crater. I'll let it start again after it goes. So this is andesitic lava. So the stuff we're looking at Kilauea is basaltic, less viscous. Andesite is stickier, and so those flows are a lot more resistant. So they don't travel nearly as fast because they're just, like I said, really sticky. And what happened here is that the first kind of signal that something was going on, there was a volcanian explosion and that's just an explosive eruption. They call them throat clearing eruptions. So that was on May 25th, 2021. And then it's been just kind of gradually filling until basically recently. So currently watching that. And cool thing to see here is what different flows from the same volcano look like. So there's a person standing there for scale, and they're standing on, you can kind of see a contact right there. You've got kind of the lighter stuff below, and then the darker kind of reddish stuff above. And the stuff that the person is standing on was a lava dome from 1974. And the stuff just above them is that lava flow that started in 2021. And so, yeah, it's a kind of a different type of lava, really cool to see, really out of the way. So a lot of the hazards with this one are just aviation. I don't think, from my look at this, I don't think that island is inhabited. I cannot remember. I'd have to look at it again. But if it's populated, it's very sparsely populated. Still want to watch out. But aviation is the main thing with this one. And so that kind of leads me to something that I'd asked my students on an assignment last term, kind of like if we're looking at volcanoes, how do we know what to expect from a volcano? We want to look at what happened before. So there can be a lot of variation with volcanoes, but usually they tend to do kind of what they've done before. I've heard somebody say about history that history doesn't repeat itself, but it kind of rhymes. I kind of think of that with volcanic eruptions too. They don't necessarily always repeat, but they might look very similar. And this picture I should have mentioned first, but this is a picture of that lava flow, the recent one, in contact with ice around the margin. So you can see that really cool pattern there. Really, really neat stuff. That's that on volcanoes kind of near us.
All right. So is it possible to map the Earth underneath volcanoes to maybe see where the magma is going and predict where an eruption may occur?
That's a good question. Yeah, and I think that's something that we always try to do. Let's see, let's find a cool picture. Just sit on here. We'll look at this one here. So there's various different seismic methods that can be used. I'm not a seismologist, so I can't remember which ones. But essentially, there's different types of wavelengths that will go through solids but not liquids, or can go through both. And so monitoring kind of seismic waves that pass through the earth, you can kind of see where things might deflect if they don't go through liquids. So that's one way. One of the things is that magmas are not always liquidy. We kind of think of a magma chamber as this just bowl of liquid sitting underneath the planet. But really only small amounts of it tend to be molten at a time. And sometimes they can be kind of little sporadic little bits that may not be very connected. But there's, if there's a significant amount of melt, they could see it that way. There's different ways, types of seismology where they can see kind of fast versus slow bodies. So they can translate that to hot or cold. So if you can see those things, then yeah, we can say, yeah, it's probably going to be here. It's just kind of a complicated thing when you're looking under the surface. Some of the seismic signals are not unique. So sometimes it's like, okay, well, this could be something hot, or it could just be a different density. So I think that people who do seismology in very active areas know what they're looking for. And so that is kind of the goal. I think I got there.
All right. Well, we've got another question along those.
Sure.
The Mt Spurr eruption, you mentioned that the island was pretty much uninhabited, but is there any risk of lahars where the lava is interacting with ice?
So I think definitely. Yeah, I think, let's see, where's the Mount Spurr? You can see that thing is covered in ice.
No,
So
the other one, the Sitkin.
Oh, Sitkin.
Yeah.
Right. Okay. So this one there are glaciers. You can see them from this one. And the lava flows are the dark bits on there. So those are the recent lava flows. I think that in times of when it's icier up there, that's definitely going to be lahar danger. It's kind of like if a lahar goes in the forest and no one's around to get in the way. Did it really make a big mess? Probably. Tried to make that analogy on the fly. I don't know if it worked. But yeah, I think that if there's ice and there's lava, and if you have especially if you have an explosive event, you kick out a bunch of tephra, which I'm pretty sure is the dark stuff on the top of the picture there. If you make that stuff loose and then you melt a bunch of the ice, then it's going to go somewhere. So definitely I think there'd be potential, but hopefully it won't cause a lot of impacts to people.
And just for all of us, what is your PhD topic?
Oh, so my PhD topic is looking at basaltic andesite lavas, or kind of just mafic lavas in the Central Oregon High Cascades. So trying to figure out why the most abundant lava type is there, why is it the specific composition it is, and kind of how is it that we get different chemical variations. It's a cool project. One of these days I'll give a full talk about it. But yeah, I've just been sampling a lot of samples to get a lot of data in an area where there's been feast or famine. If you're at a major center, there might be a lot of data, and then you'll see there's 100 cones that have nothing. So I'm trying to just beef up the chemical record and get some good geochemistry so we can try and figure out what's going on. So we're going to move on to another article. So this one is, I'm calling the segment Tracking Sediment for Coastal Resilience, looking at an article talking about sediment on the Mississippi River. So picture in the background is partly, you got some like polygons on there, but showing the Bird's Foot Delta. I've got it in like the next slide. The Delta, Mississippi Delta. So what's the problem? What inspired these people to start looking into sediment here? So essentially, Louisiana's coastlines have been receding for decades. Big problem, especially if you live near the coast. Here's a picture from Hurricane Ida in 2021. So the coastlines have been receding, and it's been leaving small towns exposed to these storm surges and hurricane winds and everything because there's just less land in front of them. So the impact from this is that the levees and other human-made structures have been kind of obstructing sediment movement and just kind of the natural flow of the sediment, not just the water and clay accumulation, things like that. Basically, what they found is that less than 10% of the sediment that kind of moves along the river is actually making it to the Bird's Foot Delta. So it is a Bird's Foot Delta. You can see why it got its name there. It's kind of like a bird foot. So that's an image from the USGS, slightly color enhanced. And so this has been a big problem for ecosystems, but also navigation, fisheries that are on the river, infrastructure, and it's really kind of putting the delta itself at risk. There's a picture of I think it's a dredge, little puttering along on the river there. Recently, in order to understand where sediment is kind of going and what it can be used for, there's a team called the Miss Delta Initiative that has been looking into this problem, and it's a $22 million 5-year research program. This is spearheaded by the Tulane University and Louisiana State University, and then funded by the National Academies of Sciences, Engineering, and Medicine. So they've been kind of looking to see where the sediment is settling and find management approaches that can kind of benefit everybody involved, ecosystems and residents. So those are some scientists taking water samples there. And the next one, we've got a drone. So what they've been looking at, they've identified sediment loss areas, kind of been looking for the places where things are more vulnerable, points either in the natural system or in man-made channels. And what they have found so far is that there's greater loss of sediment during low to average flow and then in floods. So during low or average river flow, you've got slower water that allows the heavy sand particles to sink. And then with floods, you've got faster moving water that's bringing sand in from the drainage basin, but it often falls out in the channel. So it requires more dredging instead of building up the delta. So yeah, that we've been getting some good results out of, informative results out of it. And I liked this quote from one of the professors on the project. It's that sand is white gold in Louisiana and we need to keep it. So there's some of the nice sand there on a little wetland. So yeah, the project has been kind of modeling sediment movement and looking at basically modeling all kinds of different scenarios that could happen, changing variables, looking through about 2,100 years. So year 2100. So feels like it's far away. But yeah, researchers have been kind of looking at sediment movement to calibrate their models, see what the delta's fate would be, and also to determine potential intervention options. And kind of the main points that they found there for intervention is going to be things like closing river exits, changing water flow patterns, and reducing flow in key locations. So identifying those points that were vulnerable is how they can kind of model it going forward, and also looking at sediment diversion or relocation, like moving sediment from areas where it's accumulating too much, putting it in areas where there's not enough. So that's kind of the project. It's ongoing. So that's something, if you're interested in sedimentology, that's a cool one to follow. And so that kind of wraps that up. And with that, I'm going to say that's it for June. And here's a view of the channel Scablands, and I can answer some questions.
I have a question for you on the Mississippi Delta.
Yes.
Did that article study take a look at sea level rise with respect to the sediment coming down drainage. And I have to admit, as a geologist working in the hydro world, I'm a little changing where sediment falls sometimes can be a little dicey
Mm-hmm.
in terms of relocating it.
Yeah.
And having worked with folks in the National Forest of Louisiana, sand is their gravel. That is all they have. So, yes, it is gold. It is white gold for sure.
Yeah. Well, I think that I didn't focus much on the sea level rise. I think that if they're doing their due diligence as scientists in a changing climate, um, they better be thinking about that one too. I know the emphasis was on the sediment itself. I would hope to goodness that they are considering sea level rise as well, because this is an area that is incredibly prone to sea level rise. This is an area, another assignment I just had my students do was a climate change one, looking at different types of climate data. And it is not going to cause, or it is not going to be a large increase in sea level rise. It is going to impact a lot of people. So they definitely should be looking at that. But yeah, I'll include the link in the chat after if anybody wants to take a look at that, take a little bit more of a look at the project itself.
All right. I am so looking forward to learning about the geology of Oman because when Paul Hseih said he was going to be going there, I said, would you like to talk about it? We would love to hear about it. So, Paul, are you ready to launch and tell us all about your adventure?
Okay, thank you, everyone. I'm Paul Hseih. I am a member of GSOC from the San Francisco Bay Area. And in January this year, I took a trip to Oman, a destination where I've wanted to visit for many, many years, and especially since I read John McPhee's book, Assembling California, which is all about ophiolites, and Oman is the place to see ophiolites. So I am approaching this more as a geologic photo tour with some geologic background, but certainly this is not an area of study for me. So I'm more of an amateur than a professional in this topic. So if you have questions about the details, I probably can't give you a very definitive answer, but I'll try my best. So Oman is in the eastern part of the Arabian Peninsula. On this map, it is highlighted here. And to get to Oman from San Francisco, I flew for about 13 hours to Doha in Qatar, and then changed planes, and there was a 90-minute flight to Muscat, which is the capital of Oman. So altogether, it took about 20 hours to get there. And here is a satellite photo of the Arabian Peninsula, and much of Oman is desert. But in the northeastern part of Oman is the Oman Mountains or the Hajar Mountains, and this is where the ophiolites are located. There's another less well-known ophiolite that's over here, but I'm going to just talk about this area. So, in a way, this talk is not really about the geology of all of Oman, but just the northeastern portion of it. So, first of all, what is an ophiolite? An ophiolite is a sheet of oceanic crust and mantle that has been emplaced onto continent. So in this illustrative diagram, we have the continental crust here, and ocean here, and the oceanic crust much thinner than the continental crust. The continental crust is tens of kilometers thick, and the oceanic crust is 10 or less kilometers thick. And then below the crust, we have the mantle. In the upper part of the mantle, there is a more rigid portion, which is part of the lithosphere. The lithosphere is this rigid portion of the mantle plus the crust, and that constitute a plate in plate tectonic theory. And then below the lithosphere is the asthenosphere, which is the part of the mantle that can flow, and so the tectonic plates are moving over the asthenosphere. So, in some places, a portion of the oceanic lithosphere, which is the crust and the mantle, has been emplaced onto continent, and that is called an ophiolite. So, here's a closer look at the northeastern part of Oman, and all these dark rocks are the ophiolites, also making up the Oman mountains. So the exposure of ophiolites in Oman is just spectacular. It's the world's best exposure compared to, for example, in California, there are also ophiolites, but it's a little patch here and a little patch there, whereas in Oman, it just extends for hundreds of kilometers. So I went with a travel company called Geo World Travel that's based in the UK, and they specialize in travel to geologic sites. And our travel leader is James Creswell, who's the founder of Geo World Travel. And he's done this trip, probably 5 or 6 times. So he's really familiar with the geology of Oman. So the tour was 10 days, the first and last day being travel days. So that left 8 full days to visit geologic sites. And altogether, we visited 48 sites just in the northeastern part of Oman. Many of these sites, or most of them, are geologic sites, but also included some cultural and historical sites, a few UNESCO World Heritage sites. So there's also a big part of Oman travel that's, the culture and the geology, culture and history, but I'm just going to focus on the geology. And I'm not even going to try to be thorough in covering all our stops because there's not enough time to really do that. So, just to get started, since ophiolites are igneous rocks, just to be on the same page, I just want to quickly review the different rock types of igneous rocks and how, one way of classifying igneous rocks is by minerals. So, the basic minerals would be quartz, feldspar, biotite or amphibole, pyroxene, and olivine. So these darker minerals are the minerals that are typically in oceanic crust, whereas the lighter minerals, quartz and feldspar, are a major part of the continental crust. So the mantle itself is basically peridotite, and then the oceanic crust is basically gabbro when it's as magma solidified under the ocean floor, and basalt when it's erupted into the ocean. So the oceanic lithosphere has a very clear structure. It's formed in an area of upwelling asthenosphere where you have this hot rock moving up, forming a magma chamber. And then if we expand this region here, we have this picture over here. So this part here is the mantle, and then this part here is the oceanic crust. And as the asthenosphere upwells, you form a magma chamber, and then the magma chamber feeds a magma that erupts onto the seafloor as pillow basalt. So there's a very clear set of rock that forms an ophiolite. So that at the bottom we have peridotite, which is the mantle, and then we come to the moho or the petrologic moho, which is the top of the mantle. And then the magma chamber, when it solidifies into a gabbro, And there are the magma chamber feeds these dikes that takes the magma and erupts onto the seafloor. So there's a layer of rock that's called sheeted dikes, and then you have pillow basalts. When the basalt flows into the ocean floor, it forms these pillow structures. And then not shown on this diagram is also would be some sediments on the seafloor. So this series of rock is what ophiolite is composed of. And in Oman, you can see all these rocks, very clearly, and you can go up and get right next to them. And so that's the reason for this trip. So here again, this is the stratigraphic column of an ophiolite sequence with the peridotite in the mantle, a moho. In the gabbro section, this is the solidified magma chamber. At the bottom, often there'll be layered gabbro, which is composed of minerals that have crystallized and then settled into this layered gabbro layer. And then you have the isotropic gabbro, which is most of the gabbro part. And then up top, there could be some plagiogranite. I'll show some pictures of that. And then you have the sheeted dikes, pillow basalt, and sediments. So I'll just go through the various locations where we went to see all these features. So first of all, if you Google a peridotite, uh, like in Wikipedia, you see a rock like this. So, but in the actual field, the peridotite will be weathered and it would have reacted with water. So the peridotite that we see in Oman, it looks nothing like this, but something like this, more like a serpentinite. So it's called serpentinized peridotite, which is the peridotite that has interacted with seawater and it has been hydrated so that it looks significantly different. But it's not quite serpentinite yet, so it's still called a peridotite. So here's a view of a valley called Wadi Al Kabir, which is a suburb of Muscat. Muscat is off the picture to the upper left side, and you can barely see the Gulf of Oman through the haze here. But all these mountains are all peridotite. These used to be mantle rock under the ocean, and now it's been pushed up to a continent. So you can just see these oceanic rocks, all over the place, all around Muscat. Here is a park in the outskirts of Muscat, and again, these are all peridotite mantle rock. There is a trail that you can hike up through these rocks, and if you walk up this trail, you are actually walking on mantle rock. So some of the darker mantle rocks are Hasbergite, which is one type of peridotite, and the lighter ones are dunite. But it's just really neat that we can walk on these rocks that used kilometers under the ocean floor. So above the mantle is the moho. The moho is the interface between the mantle and the gabbro, and the moho was originally defined from a seismic point of view, but here it's used to indicate difference in rock types. So the interface between the peridotite in the mantle and the gabbro in the oceanic crust is the moho. And in Oman, you can see the moho from space. So here's a satellite photo of this region is just west of Muscat. The city center of Muscat is off to the right. And so here's for distance is 20 kilometers. And this interface between the darker rock here and the lighter rock here is the moho. So the darker rock is peridotite and the lighter rock is the gabbro. And you can trace this for like hundreds of kilometers along the Oman mountains. So that's how, big the exposures of ophiolites are in Oman. Here is a well-known view. This is called the 5 o'clock the 5 o'clock moho. And this is a mountain. This is about maybe 1,000 feet. And this is called the 5 o'clock moho because in the late afternoon, when the sun shines in the right angle, you can really see the difference between the peridotite, which is down here, and the gabbro, which is up here. And the moho, or what used to be the moho under the ocean, is right along here. You can get really up close to actually touch the moho. This is another fairly well-known site called Wadi El Abjad. And here the moho is kind of displaced by faults, but it is still well indicated with peridotite here and gabbro here. And you can actually, scramble up this hillside and put your hand right on the interface between the mantle and the crust. So just above the moho is this layered gabbro. This layered gabbro is what you get when minerals in the magma chamber crystallizes and falls down and then make this layered texture. And it is fairly unusual because generally igneous rocks don't have layers, but you do see this in the layered gabbro. So right near where we saw the moho, you can see this layered gabbro. And this layered is formed by the settling of the olivine, the pyroxene, and the plagioclase minerals in a fashion where you end up seeing these layering. And in this card, one of these squares is a centimeter, so that gives you a little scale. If we go further up the gabbro section of rock, we get to sometimes we can find these rocks called plagiogranites, and it usually occurs in the transition between in the gabbro and the sheeted dikes, and it's sometimes also called Trondhjemite, Trondheimite. I've heard it pronounced different ways. I'm not sure which is the correct one. But basically, it's composed of plagioclase and quartz. So among this dark rock, you see this very distinctive, very light rock that's created from basically fractional crystallization. So here is outcrop of this plagiogranite, and you're surrounded by all this dark rock in the Oman mountains, but then you see this very distinctive sharp contrast of white rock. And if we zoom in, here's the tip of a pen. The white stuff is basically plagioclase and quartz, and then these dark minerals are biotite or amphibole. So a very neat contrasting rock within the usually dark ophiolite. So next we come up to the sheeted dikes, and the sheeted dikes, when we think of dikes, we usually think of like a channel of magma going through a country rock. But here, the sheeted dike is all dike rock. So basically, as the seafloor spreads, the magma chamber will feed a dike, and then the dike cools, and then the next time that you have another episode of molten rock coming through, it will push apart the existing dike to create a new dike. So after many millions of years, you have this entire rock that's just dike. So it's dike going through dike rocks. And a very characteristic feature in sheeted dikes is what is called a chill margin. And the chill margin is where when the hot magma goes through the chamber, goes through the channel, it touches the existing cold, previously solidified dike, and you have a very quick chilling of the edge of this conduit, and you get this very glassy texture. Whereas in the center of the conduit, you have more time for the magma to cool, and so you have larger crystals. So this chill margin is a very characteristic feature in this sheeted dike. And so here is one place where these are all dike rocks. They've been kind of tipped a little bit, but basically they're all rocks in the sheeted dike complex. And if we look in a little closer, you can see these chill margins in the dike rocks. And then finally, we get up to the pillow basalt. And when the magma erupts into the ocean, it forms these pillow patterns. And here's a little video that shows how as the magma flows onto the ocean floor, the outside immediately crystallizes, and then it breaks open, and you get these pillow structure. And in Oman, we have probably the world's best outcrop of pillow basalt. This pillow basalt is called the GeoTimes pillow basalt because it was featured on the cover of GeoTimes magazine, which is now defunct, back in 1975. And in this outcrop, also, you can actually see a couple of dikes where the magma came up through the already solidified basalt to erupt further up in the ocean floor. And if we look into one of these dikes, we can actually see again these chill margins. So it's repeated flow of magma through this channel, and here's just a blown up portion of this dike, and you can see the chill margin here. So this was the previous dike, and then this is, the dike that went through the previous one, creating the chill margin. And so finally, we have the sediments here. And this is another well-known site in Oman. These are sediments this is actually sediments that's not directly over the Samil ophiolite, but they form this really beautiful layered sediments and then it's been deformed since the rock was placed onto the land surface. And so here's just for scale, this area here is in this picture here. Oh, okay. So I just want to finish up with talking about how this ophiolite was formed and emplaced. So the ophiolite was formed about 100 million years ago, but to get the picture started, here's a reconstructed map of Pangaea 200 million years ago. And as Pangaea breaks up, Africa here with the Arabian Peninsula here will move towards Eurasia, and this is Oman here. And as Oman moves over towards Eurasia, the ophiolites form in the ocean, and then it's abducted onto the continent. So here's a quick animation going every 20 million years. So at 180 million years, Australia and Antarctica is separating, South America and Africa is separating from North America. And as we move along, at 100 million years, here is the Oman ophiolite is kind of forming in this Neotethys Ocean out here. And then at about 80 million years, it's starting to abduct onto the continent. And then you have the Tethys Ocean closing up and the Red Sea opening up to the current day scenario. Okay, so there are actually two models of how the ophiolite formed. One is the mid-ocean ridge model, and one is the supra-subduction zone model. So the mid-ocean ridge model envisions that you have a mid-ocean ridge in the Neo-Tethys Ocean between Eurasia and the African plate, and then this part of the ocean floor eventually gets abducted onto the continent as this region closes up. Whereas the supra-subduction zone model has an actual subduction zone, and then the subduction causes a mantle upwelling, and that creates a magma chamber, and then creates the semi-ophiolite, and then eventually again it's abducted onto continent. So the difference between these two is that the chemistry of the ophiolite, or the chemistry of the basalt, will be different. And I think currently the supra-subduction zone model has stronger support for it than the mid-ocean ridge model. So, and that's all I'm going to say about it, because I really don't know enough about how these basalts are analyzed in terms of geochemically. I know they look at these patterns of incompatible elements and so on. So maybe Alyssa can tell us something about that. But another really interesting idea is how the ophiolite was abducted onto continent. And again, there are two ways to think about it. One is that the ocean lithosphere got thrusted over the continental crust. This is kind of the traditional interpretation. But a new interpretation actually has the continental crust being pulled under the oceanic lithosphere, which is something that, whoa, like we know that, or we are taught that continental crust is lighter and can't go under a lithosphere, can't go under an oceanic lithosphere, but ideas are changing. So, and again, this idea has a substantial amount of evidence to support it. So the idea being that at about 800 million years, the continent of Africa, Arabia, has now come to the subduction trench. And you have the old Neo-Tethys ocean floor being pulled down. And this is actually pulling the continental crust down underneath the oceanic crust here. And as that happens, the continental crust is pulled down, stretched, and then at some point the slab breaks off. And when the slab breaks off, the continental crust jumps back because it's lighter, and the buoyancy pulls it back. And as it's being pulled back, all these rocks are being crumbled up, and over a fairly short period, it jumps back up. And this is kind of close to the situation today. There's some erosion going on, and the kind of the current day cross section will have, the ophiolite here, and with the continental crust kind of bulging over here. And on this side here, we have all these folded sediments that we can see. So do the last few pictures showing some really big scale folding. There's a sheath fold that if you cut it, you see these eye-shaped features that you can also see. This picture is taken looking into the sun, but you can see these kinds of very large structures. And there are a bunch of other structures, but I've run out of time, so I'm going to stop here. This is a Triassic limestone that's sitting on top of volcanic rocks. So this is actually a submarine volcano with an atoll on top of it, and it was scraped onto the continent due to this abduction process. And up here are these beehive, what are called beehive tombs that are of early Bronze Age, about 3000 BC. So I'm going to stop here. Oman is just a wonderful place. If you have a chance to go, I definitely highly recommend it. Thank you very much.
Oh, Paul, that was exactly what I was hoping for. And I know folks were chatting about, so you ready to take off on an adventure? For me, that was the adventure I was looking for. Thank you so much. So, and I think Carol's question was answered. She wanted to know what the tectonic driver for the exposing the ophiolite and how old it is. So I think you've got the driver question. So because of these other ideas, is that pulling back, is that making the time younger than everybody thought? It's not 200 million, it's more like what?
Oh, the ophiolite was formed around 95 million years ago. That was dated from the basalt, and so that number is actually considered to be pretty accurate. And then it was abducted onto the continent at about 80 to 70 million years. And then there was erosion and things like that. But so basically the whole process went from about 95 million years to 70 million years.
Next question here is the Coast Range ophiolite by the Bay Area has bluish, greenish blue serpentinite, but the Oman ophiolite looks brown and rusty. Is that just due to erosion and chemical weathering of the rock or some chemical composition differences, serpentinite versus peridotite?
The brown, the prototype actually has this brown looking color. So this is like this picture. So all this brown hills are prototype. And apparently it's due to the dry conditions in Oman that these mountains are still in place because in a humid climate, prototype weathers very quickly, all these might be gone. So in the Coast Range ophiolite, I don't think we see very much prototype. Mostly it's the gabbro, the sheeted dikes, and the pillow basalt.
All
Can I
right.
butt in just a tiny bit?
Yeah.
Because I actually know a little bit about the Bay Area. So I think that the blue schist or the blue serpentinite stuff that you're thinking about is actually from the melange, and so I think that's separate from the peridotite, from the ophiolite. So it's its own special kind of mess, if I'm not mistaken.
Yeah, also the peridotite has all turned to serpentinite. So
Mm-hmm.
we have beautiful serpentinite, which is this greenish, a slightly bluish rock. And then we have these rocks called blue schists that have kind of gone down the subduction zone and somehow found their way back up to land surface.
So, Paul, quick question here. And it's great you've got this image up here. What are all these lovely buildings built with? Are they, now that I saw that limestone, are they coming in from the limestone, or did you kind of get a sense of what they were constructed with?
I, I don't know. I can't answer that question. I
Okay,
mean,
that's okay. I was just
yeah.
looking at them. There's such a contrast to the mountains. Okay, moving on with the questions. I'm obsessed with mantle geology, geodynamics, so it's a treat to see your photos of the Oman ophiolite that you rarely find online. So kudos, Paul. Thank you very much. Okay, what concessions do visitors to Oman have to make culturally, especially for women? What was the biggest cultural faux pas to avoid?
Well, if you visit a mosque, you have to so you have to cover your head. Generally, the the advice is to dress modestly. But other than that, I didn't experience. I mean, there were quite a number of women in our tour group, and I think they were all very comfortable being in Oman, and people are very friendly, so I don't think it's a big worry.